students, welcome you all for the other lecture on the course Computer Architecture and Organization. In today's class, I am going to discuss about the concept bus arbitration. From last few classes, I discussed about different IO techniques. In that, I discussed about programmed controlled IO, interrupted driven IO, and the third one is direct to memory access DMA. And coming to today's class, I am going to explain about the concept bus arbitration. So basically, there are two different types of bus arbitration methods used in our system. In that, the first one is centralized bus arbitration, and second one is distributed bus arbitration. Before discussing about these two different varieties of bus arbitration, first we have to go and learn about what is bus arbitration. Later we will go and discuss those two methods. So I welcome you all for this course. Right. So processor and DMA controllers both need to initiate a data transfers on the bus and access main memory. Just you remember the last class in direct memory access DMA concept. Your DMA controller is act as IO module as well as IO interface. And for the DMA controller, we are connecting number of IO devices or external devices. And your DMA controller other end is connected to the system bus. And to the system bus, processor and memory elements also connected. Whenever any IO device want a direct data transferring with the memory elements, that IO device send a request to a DMA controller. Then DMA controller took the permission from a CPU to use the system bus. For that purpose, our DMA controller issues a request signal to a CPU, which we can call as a DMA request or a hold request or bus request. Once your CPU receives that request, your CPU gives highest priority to it and it immediately responds to it by sending off acknowledgement back to the corresponding device, as well as it releases control over the system bus. So later onwards, the system bus can be used by the DMA controller. It can provide a communication between an IO device and the memory elements. So here what I am saying is, if you go and take a system, memory, processor and DMA controller, all these three devices are directly connected to our system bus. At any instant of time, our processor and DMA controllers both need to initiate data transfer on the bus to access main memory. Coming to the second one, the device that is allowed to initiate transfers on the bus at any given time is called bus master. That means at any instant, the device who initiate data transfer over the bus, that particular device what we can call is bus master. For example, let me mention guys, this is a bus. So for this bus, I was connecting, this is my CPU and this is memory, and here I have a DMA controller 1 and this is a DMA controller N. So DMA 1 and DMA N, and there we are connecting a number of IO devices like this. So the connections are like this in your system. So this is a bus. So always the CPU and the DMA controller want to try to communicating with this memory with the help of this bus. This is the first point. And the second point, for example, at a time incident T1, in time incident T1, the CPU initiate data transfer. That means this CPU transfer the data to the memory. So then automatically I assume that the CPU is called bus master. So I clearly told you guys, the device that is allowed to initiate transfers on the bus at any given time is called bus master. When the current bus master relinquishes its status, that means if the CPU finishes its data transfers, then it releases a control over this bus. Then automatically what happens is the remaining devices which are present in the system, they try to access that bus. So that is the meaning of this. When the current bus master relinquish its status as the bus master, the other device can acquire this status. Right. Next, the process by which the next device to become the bus master is selected and the bus mastership is transferred to it is called bus arbitration. So what is the meaning of this? Here we are using a particular process to go and select or to go and choose a next device which becoming as a bus master. This whole process what we can call is bus arbitration. So basically I already told you there are two types of bus arbitrations. One is a centralized bus arbitration and second one is a distributed bus arbitration. What happens in case of this centralized arbitration? In case of centralized arbitration, a single arbiter circuit will assign a bus arbitration process. I repeat, in centralized arbitration, a single bus arbiter performs this arbitration process. But coming to the distributed case, all the devices which are present in the system, they are involving in this bus arbitration process. That's why it is called distributed bus arbitration. In case of first, that is a single bus arbiter can do bus arbitration process. That's why it is called centralized bus arbitration. In case of second one, in a distributed case, in the case of all the devices which are present in your system, they are involving in the bus arbitration process. That's why the second one is called a distributed bus arbitration. So we can go and discuss much more about this centralized as well as the distributed bus arbitrations. So coming to this, the simple structure which represents centralized arbitration or centralized bus arbitration. See here friends, this is our processor. So this is the DMA controller 1, DMA controller 2 and so on. The number of DMA controllers are connected. Let here you assume each and every DMA controller just acts like an I/O module or I/O interface. It acts like I/O module or I/O interface. And here we are using three different signals. One is a BBS1 bar, which means bus busy bar. This is active signal. And second one is BR bar, that means bus request bar. It is also active signal. And next one is BG. It means bus grant, which is active high signal. So here important thing is the DMA controllers in this system, they are organized like a daisy chaining fashion. So we know that the daisy chaining connection, in that connection our processor or the CPU issues acknowledgement signal to the nearest device. The nearest device in the sense from that CPU or a processor point of view, that device have a highest priority. And with that responsibility of that device, if the device can't send any request to the CPU, it simply bypasses the received acknowledgement signal to the next. So here important thing in daisy chaining fashion is, it is the responsibilities of the devices. They bypass the received acknowledgement signal which is issued by the processor from one device to another device. So here important thing, the process is like this. So in case of this centralized arbitration process, so a central arbiter or a single arbiter, generally a single arbiter who do the arbitration process, that may be a processor or a specialized device which we incorporate in the system. So let's go to the previous slide guys. So what is centralized arbitration? A single bus arbiter performs this arbitration. So single bus arbiter, that arbiter may be either your processor or it may be a special circuit which was connected to your bus. In maximum cases, in case of centralized bus arbitration, the single arbiter is nothing but a CPU or a processor. So here the devices, that means your DMA controller 1 or 2, they are sending the request signal to CPU to use the bus. In the process, this DMA controller send their request signals with the help of a common signal which we can call as bus request. Whenever your CPU identifies logic 0 or this, it identifies that I received some request from the IO devices, some device got a bus. Then what your CPU can do is, it will send acknowledgement signal to the nearest device. That means the CPU send acknowledgement signal to the highest priority device from a CPU point of view. So here I assume that that signal is BG1. If this signal is received by the DMA controller, originally this DMA controller can't send any past request signal. Then what this DMA controller can do is, it simply bypass the received acknowledgement signal which it receives from the CPU end to the next one, that here we can call as BG2, bus grant 2. If this is the device which actually send a request to the CPU for the purpose of bus, then automatically once it receives a bus grant signal, automatically it will go and use the bus. That means this device now becoming as new bus master. But here important thing is, before sending a request by these devices, first these devices go and investigate what the logic level that was going on BBSY bar signal. Because here this BBSY bar is nothing but a bus busy signal. Whenever these devices identifies logic 0 or this, that means already the bus was busy. That means already the bus was used by somebody else. So that information these devices are getting by investigating this particular signal. So whenever these devices identifies the logic level on BBSY bar changes to 1, that means the bus is free. That incident, these devices are trying to go and get the bus authorship or a bus mastership. So for that purpose, they are sending their request signals. So here important thing is, the whole arbitration process is done by this processor, because this processor collects request signals from all the DMA controllers. So this is the simplest first bus arbitration method, which is centralized. So next one is distributed arbitration method. In case of this distributed arbitration method, what happens is, all the devices which are present in the system, they are involving in bus arbitration process. So in previous case, we have a single arbiter circuit, which may be a processor or it may be a special circuit, which collects request signals from all the devices, and it will assign the services for those devices. But coming to this, in case of a distributed bus arbitration method, all the devices which are present in the system, they are involved in bus arbitration process. That's why it is called a distributed bus arbitration. So this arbitration process does not depend on centralized arbiter, and hence the distributed arbitration has higher reliability. It's important. The reliability of this distributed bus arbitration method is high compared to centralized. Why? Because in case of this distributed bus arbitration method, there is no centralized arbiter to assign the buses to different devices who are sending their request signals. So the relative reliability of this distributed bus arbitration method is high compared to centralized. So how it will be happen, that we can go and check it. But here I consider an example. For example, what are the devices I have in my system? I assign an identification number to each and every device. That identification number size is a 4-bit. That identification number size is a 4-bit. So that's why here I written as each device is assigned a 4-bit ID number. So here I took an example. In my system, I assigned 4-bit identification number to each and every IO device which was involved in bus arbitration mechanism. So all the devices are connected to using 5 lines. 5 lines. Out of those 5 lines, 4 arbitration lines to transmit their ID, and 1 line for start arbitration signal. So in a total arbitration process, there are 5 signals are used by the devices. In the case of 4 signals are arbitration signals. By using those 4 signals, the device sends their identification number, and they are sending identification number. Before that, they are issuing a fifth signal, that is a start arbitration signal. So the request the bus a device. So what generally a device can do to go and get a bus. So for that purpose, accepts the start arbitration signal first. Thereafter places its a 4-bit ID number on arbitration lines. So for better understanding, see guys. So this is arbitration mechanism. Just you can mention this is an interfacing circuit for a device A. For example, here I have a device A. For that, this is an interfacing circuit. For example, that device here has an identification number which is 5. So its equivalent binary value is 0101. So whenever this device A want to use a bus, that means a device A becoming as a bus master, for that what it do is it will send it request signal. So by sending it request signal, in that process first what it do is it will activate this start arbitration signal. So by sending of this start arbitration signal, it start sending it request. Later it will send it identification number over the remaining arbitration lines. Here we have ARB 0 bar, that means arbitration 0 signal, arbitration 1 signal, arbitration 2 signal and arbitration 3 signal. With the help of these 4 arbitration lines, the devices they are sending their request signals. Now listen carefully guys here. For example, in time incident T1, device A whose ID number is 5 and device B whose ID number is 6. These are 2 devices want a bus, that's why they are sending their request signal. So they are sending the request signal first, they are activating this start arbitration. Later they are sending their identification number. So here device A identification number is 0101 and device 6 identification number is 0110. So like this, whatever the devices they want a bus, they are sending their request signal. In that process first they are activating this start arbitration signal, followed by they are sending their identification number or these arbitration signals. So once it happens, immediately what happens is, what are the addresses they are placed over these arbitration lines, all those are logically ordered. That means these are 2 devices wants a bus. That means these 2 devices are involved in a competition to go and get a bus. That means these 2 devices send their request signals to get a bus mastership. So that's why these 2 devices activate this start arbitration signal, followed by these 2 devices send their identification number. Then what happens is immediately the values who are present on these arbitration lines, there is a logical OR operation is performed over those lines. So that means we are doing logical OR between these 2. Then what happens? 1, 1, 1 and then 0. This is an outcome of logical OR after sending all the devices their identification number. Then what happens is, this is the consolidated arbitration value that can be presented over this, that can be received by all the devices. See here guys, this is an interfacing circuit for a device A which collects this consolidated code over this. So this is received by this 0, 111. What's the meaning of that? Your device A and device B want a bus. That's why they are sending their request signals by sending up their identification numbers. Here we are doing a logical OR operation between those 2 numbers. That's why we are consolidated code. What we are getting is 0, 111. Now this is received by your interface circuit of device A. Then what happens here is, once this code is received by device A, then start the device A compare its identification number with the consolidated code what it receives from arbitration lines. Its identification number is 0101 of device A. What it do is it receives consolidated code, that is 0221. Then your device A start comparing of these 2 codes. That means the device A comparing its ID number with consolidated code. So from most significant bit onwards. So here both the bits are same. It didn't do nothing. Here also both bits are same. Here we do nothing. Here we are doing. But if you are coming to this third bit, what happens is there was a difference. Coming to bit position 3, there was a difference. Because in identification code of a device A, there is a bit was 0, but received in consolidated code, in the same position we have a bit value is equal to 1. Once this is the scenario, once we are identifying the difference at any bit position, from there onwards, the bits are becomes 0. The bits are become 0. That means your this value 0 and this value 0. That means your device A removed from the race. That means your bus is not dedicated to device A. This is a new consolidated code that was present. Now this code is received by device B. This device B code is again comparing with this. Then what happens? 0, 1, 0, 1, and it is again 0. Logical. First do logical AND. Logical AND between this. Consolidated code and its identification number. Then what we are getting? 0, 1, 1, 0. So what this is equivalent to? This is equivalent to device B. This is equivalent to device B. That means out of these are two devices. That is a device A and device B. The device B win the race. That means the device B now becoming as a new bus master. Or I can see in another way. So this is the consolidated code that can be received by both the devices. In that process, what happens is device A absolutely removed from the race because third bit difference. Coming to device B case, device B identification number is 0110 and then received consolidated code is 0111. Now we compare 0, 1, 1 and here there was a difference so it becomes 0. Now the produced code is equal to 0110. Again that is belongs to device B identification number. That means in this particular race, in the race both the devices A and B are involved to go and get a bus mastership. But at the end what happens is the device B win the race and new bus master of your system is device B. So like this, in a distribution bus arbitration method, the devices get a bus mastership. So generally if you think guys, this is very simple logic. The logic is like this. If a device want to go and use the bus, that inform to the rest of the devices. That means there is a discussion is going on between the devices which are involved in that bus arbitration method. Finally only one device get a permission from the remaining devices and that device becoming as a bus master. So compared to centralized, here there is a chance all the devices get a chance to go on becoming as a bus master in the system. So that's why this second method is the best compared to the first method. I hope you understand friends what this both the methods are, centralized as well as the distributed bus arbitration methods. I hope you understand this. In the next class I am going to discuss about another new concept in this course. Thank you for patient listening. Thank you very much.